Hundreds of meters of rock exert colossal pressure on the cutter head of the boring machine. Metal collides with geology in the depths of the earth. Why do engineers bore through these hazardous zones? The darkness surrounding the equipment is absolute. This method allows for the connection of two worlds through colossal tunnels. But this is just the beginning of the task. One can notice how the steel components rotate ceaselessly within the mountain's shadows. Every meter drilled requires precision engineering to ensure structural integrity. The mechanism turns geological resistance into progress. At first glance, it seems like brute force, but in reality, it is a strictly calculated process. What was once a technical dream has become proof of human ingenuity. The force drives the equipment into layers where no one has gone before. It gets more complex further on. The machines keep turning, carving pathways to the future. The process continues its steady motion forward. Over 1,000 deadly landslides are recorded annually in China alone. This grim statistic reveals a harsh physical reality hidden behind the visual majesty of the mountains. In 1991, a catastrophic landslide at the Racha Pass claimed more than 200 lives. In 2014, a fierce snowstorm in the Annapurna Range left 400 trekkers missing. But this is just the beginning of the challenge. These events drive the relentless search for a safer path. Why do engineers choose to bore directly through the rock? At first glance, following the natural contours of the mountain passes seems like the logical route. But in reality, tunnels provide the only guarantee against surface instabilities and extreme weather conditions. Massive tunnels allow vehicles to travel straight through the geological barrier instead of winding along dangerous precipices. One can notice how the linear trajectory significantly cuts travel distance compared to surface routes. Engines operate at consistent loads on flat gradients, saving fuel and reducing harmful emissions. The process is only gaining momentum. Peril transforms into calculated industrial safety. Rugged peaks turn into vital arteries for modern logistics. This engineering strategy effectively conquers the vertical landscape. The global transportation map is redrawn as traffic moves securely through the mountain base. 300 meters is the depth to which exploratory drills sometimes penetrate the mountain. To turn the dream of tunneling into reality and redraw the map of global transportation, every project starts with a plan detailed down to the smallest element. After determining the route to be connected, engineers begin the first stage, known as a comprehensive geological survey. But this is just the beginning. Why is it necessary to extract samples from such depths? One can notice how machines bring up cylindrical cores of stone from the boreholes. Each sample helps them better understand the mountain's internal structure by measuring hardness, porosity, and groundwater pressure. At first glance, the terrain looks stable, but in reality, engineers must pinpoint fault zones, weak rock layers, and areas prone to landslides. Simultaneously, environmental specialists assess how the project might affect the surrounding landscape. They analyze erosion risks and changes in underground water flow to minimize impacts on nearby ecosystems. It gets more complex further on. The data enters the digital processing phase. All information is fed into three-dimensional geotechnical simulation software. It is visible on the screens how the team effectively sees through the mountain to calculate the optimal slope, alignment, and curvature radius. From these measurements and simulations, the safest and most efficient construction plan is finally chosen. Hundreds of meters of depth create a zone where pressure and heat become critical factors. Why must the ventilation system be established before any other major work begins? Amid dense rock and heavy darkness, the environment is unforgiving. Without a controlled air supply, stone dust and rising temperatures can make the atmosphere toxic within minutes, forcing engineers to create an artificial network. One can notice how the project effectively takes its first breath once this system activates. Vertical shafts are drilled from the construction center upward to the surface using the raise boring technique. It is visible how the drill head is operated from inside the tunnel, pushing against the rock toward the sky with near-perfect precision. Each shaft spans 4 to 6 meters in width and extends up to 200 meters in height. At first glance, it seems like a simple channel, but in reality, active management is required constantly. Sensors inside monitor oxygen levels, temperature, and toxic gases without pause. They coordinate powerful jet fans that expel exhaust and bring in fresh air. But this is just the beginning of the safety protocols. The entire network becomes the lungs of the project, allowing hundreds of workers to labor for hours. 1,500 tons, exactly the weight of just the cutter head, the heaviest single component of the tunnel boring machine. Outside, the construction site is shrouded in a dense haze of dust, while deep inside the mountain, a true symbol of the modern infrastructure era slowly takes shape. Why is this colossal machine assembled in cramping underground conditions rather than on the surface? It seems logical to build it in a spacious factory to avoid complications, but the sheer size prevents transport, forcing a complex delivery of the system via hundreds of specialized transport vehicles. Each truck carries modules weighing from dozens to hundreds of tons to the assembly point. But this is just the beginning of the logistical challenge. Engineers widen auxiliary tunnels to create the necessary room for these massive components to pass. One can notice how the rock walls are temporarily reinforced with heavy steel beams and thick layers of sprayed concrete to ensure safety. Positioning this giant for its first operation demands absolute precision from the team. At first glance, shifting such mass seems like a crude industrial task, but in reality, it requires the delicate coordination of hundreds of engineers. Powerful hydraulic jacks lift the cutter head, which spans nearly 15 meters in diameter, into its precise position. The mechanism links step by step with the body and tail sections according to a strict predetermined sequence. It gets more complex further on. In the confined space, hundreds of industrial lamps illuminate the metallic surfaces, banishing the underground darkness. Because the machine must operate as one, the modules are connected with zero room for error. Laser sensors monitor the alignment process, allowing a tolerance margin of no more than 5 millimeters across the entire structure. From the complex hydraulic systems and control cabin to the supporting frame, thousands of mechanical parts are perfectly fitted together. And this is not the limit of the engineering feat. Once fully assembled, the entire tunnel boring machine stretches nearly 100 meters long. This length is the equivalent of a 30-story building laid on its side. The unified steel giant is now fully prepared to pierce through the solid heart of the mountain. Over 3,000 tons of massive machinery come to life with a single command from the central control cabin. The electrical, hydraulic, and pneumatic systems activate in unison, causing the mountain to tremble slightly under the sheer power of the awakening mechanism. The tunnel boring machine, stretching nearly 100 meters in length, begins its slow but relentless advance deep into the earth. Thousands of mechanical components work in perfect harmony to drive this giant forward. But this is just the beginning of the operation. Why is such immense pressure required to move forward only a few feet at a time? To the naked eye, the forward motion appears almost imperceptible against the vastness of the rock face. Without this calculated force, the cutter head would fail to penetrate the geological layers effectively. 4 massive hydraulic cylinders press the head against the rock with a pressure of up to 500 tons, ensuring the necessary friction for excavation. 23 alloy discs spin with immense torque at the front of the shield, grinding through the obstacle. One can notice how layers of rock, as hard as steel, fracture and crumble under this mechanical assault. Each drilling cycle advances the tunnel by approximately 1.2 meters, a process that takes roughly 30 minutes of continuous grinding. engineers repeat this sequence more than 50 times per shift. It gets more complex further on. Crushed rock falls onto an automated conveyor, which carries the waste away from the excavation zone without pausing. At first glance, the rotation of the head seems like a chaotic grinding process. But in reality, high-pressure water jets are constantly at work to cool and clean the cutting surface. This liquid stream reduces friction, preventing the machine from overheating deep underground, while the rear section is still being assembled in the launch chamber. Precise coordination of power, water, and air systems ensures everything runs without interruption. Once a cycle ends, the gripper shield pushes forward to reset the position, and hydraulic clamps lock firmly onto the tunnel walls. This rhythm, press, release, advance, drill, repeats endlessly, day and night. Monumental projects like the Santa Lucia Tunnel in Europe utilize machines with a diameter of nearly 16 meters, while the 57-kilometer Gotthard Base Tunnel in Switzerland operated 24 hours a day. Yet today, China leads this underground frontier with over 1,000 machines simultaneously carving railways, subways, and hydroelectric tunnels. This scale serves as a true symbol of determination to conquer the depths with technology. The complex mechanism continues its journey, leaving a reinforced tunnel in its wake. 5 to 6 meters is the depth of the boreholes drilled into the rock face when modern machines hit their limit. Although the tunnel boring machine has ushered in a new era of modern construction technology, not every type of geology is suitable for this colossal machine to operate at full efficiency. In areas with soft, porous, or unstable rock layers, even the slightest vibration could trigger a catastrophic collapse. Therefore, engineers must return to a seemingly old yet time-tested method known as controlled drilling and blasting. This technique requires a sophisticated blend of rock mechanics, explosive chemistry, and the highest level of safety control. But this is just the beginning. The process initiates with a detailed geological survey, seismic measurements, and determination of safe vibration limits. Why rely on explosives in such delicate environments? At first glance, using dynamite in unstable soil seems counterintuitive and dangerous compared to automated boring. But without the precision of a calculated blast, the continuous vibrations of a machine would shatter the fragile rock structure, making safe extraction impossible. The construction team drills hundreds of holes, arranged in a strict fan pattern to direct the explosive energy evenly through the rock mass. One can notice how the drill bits bite into the stone, preparing the network for the charge with mathematical accuracy. Before every detonation, all wires and electric detonators are checked for resistance to prevent leakage or short circuits. Geological data is fed into three-dimensional simulation software to precisely calculate the amount of explosive. It gets more complex further on. Calculations determine the delay timing between each blast point, ensuring the explosion propagates in a controlled direction. Each hole is loaded with 80 to 100 kilograms of explosives combined with fast and slow-reacting chemical agents. This mix ensures the blast unfolds in a preset sequence rather than a chaotic burst. When the warning signal sounds 3 times, the ground shakes and the rock shatters exactly as designed. Dust slowly settles, revealing the fragmented stone. Immediately after the explosion, 2 high-power ventilation ducts are activated to extract toxic gases. Everything only gets more complicated. About 20 minutes later, the engineering team enters to measure tunnel wall deformation and clear loose debris. They spray a temporary layer of shotcrete to stabilize the rock ceiling against gravity. At first glance, this cleanup seems routine, but in reality, it demands absolute precision to prevent cracks or water leaks. Even a slight miscalculation could cause total collapses. That is why modern tunneling projects now integrate vibration sensors, digital simulations, and real-time monitoring. The camera glides along the secured walls, showing how this traditional technique works alongside modern equipment. Thus, the method maintains its irreplaceable role in contemporary tunnel construction. 1 to 1.5 meters of rock are removed in a single excavation step. Why move forward with such cautious slowness? Traditional drilling and blasting methods prioritize speed above all else, but they reach their limits in weak geological zones. But this deliberate pacing is key to the new Austrian tunneling method, or NATM, developed in Europe during the 1960s. One can notice how the design philosophy shifts from resisting nature to working directly with it. The technique harnesses the natural load-bearing capacity of the ground itself to carve pathways through mountains. Instead of relying entirely on artificial support structures, the surrounding rock mass transforms into an active part of the tunnel's structural system. But this is just the beginning. Excavation proceeds in short, controlled sequences to maintain safety in complex environments. At first glance, applying concrete seems like a simple finish, but in reality, it is a critical structural intervention. Immediately after digging, a 25-centimeter layer of sprayed concrete covers the roof and walls. Rock bolts and steel mesh are then installed to distribute stress effectively. The equipment gradually seals the surface, creating a natural load-bearing arch between the rock and the concrete. Because the geological stress must reach equilibrium before the final phase begins. Engineers monitor the tunnel using hundreds of sensors attached directly to the walls to measure deformation, stress, and displacement. It is visible how data streams transmit to a central control room where specialists analyze every fluctuation in real time. They adjust construction methods accordingly, adapting to even the smallest changes in the rock. Therefore, once the surrounding stress stabilizes, the permanent lining is built using cast or high-pressure sprayed concrete. This method reduces reinforcement materials by 30 to 40% while minimizing vibration and surface settlement. Such precision is crucial for tunnels near residential areas or existing infrastructure where stability is paramount. And this is not the limit. This approach solidifies the tunnel structure, marking a major advance in engineering history. 10 megawatts of backup power await the command to engage deep within the mountain. The heavy drilling has stopped, but the work is far from over. Engineers quietly enter the tunnel, carrying measuring instruments instead of drills. One can notice how they examine the walls, where every meter of concrete must prove its strength. But this is just the beginning. Why do pressure sensors and ground-penetrating radar scan for cracks thinner than a hair? At first glance, such precision seems excessive. But this rigor detects invisible flaws before they become dangerous. High-frequency ultrasound and 8K optical cameras inspect every bolt and seal to ensure flawless safety. In the control room, hundreds of real-time indicators track the jet fans, the tunnel's lungs, along with smoke sensors and drainage pumps. It gets more complex further on. All systems are tested under strict NFPA 502 and EN 50545 standards. It looks obvious to record data, but in reality, every reading and vibration is analyzed until perfection is reached. Only then is the tunnel declared ready, a true symbol of precision and human resilience beneath the earth. 1,500 sensors are embedded along the tunnel walls, continuously recording data on vibration, pressure, humidity, and leakage. Why is such a dense network of monitoring devices necessary? The tunnel enters its full operational phase as the first vehicles begin to pass through, requiring absolute precision in every system. These sensors provide constant updates to ensure safety. But this is just the beginning. Information is transmitted instantly to the control center for processing. At first glance, the structure appears static, but in reality, it is subject to minute shifts. Intelligent monitoring software analyzes the data to issue early warnings if it detects even a 0.2 millimeter deformation in the concrete structure. One can notice how the 200 kDm jet fans are inspected and cleaned to maintain peak performance. Maintenance teams also recalibrate lighting systems, smoke detectors, signal boards, and cameras on a strict schedule each year. It is visible how technicians adjust these components. The process is only gaining momentum. Because flow is critical, drainage channels over 1.5 meters deep are regularly cleared of debris. 1,000 liter per minute pumps are tested to handle heavy rain scenarios. Therefore, maintenance work usually takes place at night, when traffic flow drops below 20%. This minimizes disruption for drivers passing through the corridor, leaving the system ready for the next cycle. 0 millimeters of deviation is the strict parameter engineers maintain when the boring machine breaks through the final rock layer. Natural light penetrates the deep gallery for the first time, signaling the physical completion of the excavation phase. This technical milestone is essential for minimizing disruption for future drivers who will utilize this route. At first glance, the breakthrough seems like a momentary event, but in reality, it represents the sum of years of geodetic research. Laser systems scan the geometry immediately. Why is the entire assembly measured again to the millimeter? Visual inspection suggests the tunnel is already physically connected and complete. But absolute precision is required to confirm that the excavation axes match perfectly according to the preliminary data. One can notice the surveying equipment position to verify the final coordinates of the joined sections. The successful breakthrough serves as technical proof of the collaboration between heavy machines and precise planning protocols. Every decision made by the engineers is now validated by the physical reality of the tunnel structure. But this is just the beginning. The facility stands ready for the installation of safety systems,